Now, the solution is not that difficult. For example, if I take another derivative of this one, then it will become y triple dot. This will become omega z double dot. Now, omega is a constant, and this will come out to be z double dot. And then for the z double dot, I put this way, and this is d cube y over dt square, and here it will be dy over dt. We will solve this differential equation, and don't worry about the solution of this differential equation. I'm not going to solve it here because it will consume a lot of time, but I will provide you with the lecture notes. In the lecture notes, I have solved this couple of differential equation, and you can easily follow all the steps from there. I will rather write the solution directly in the form of constant. So the y of t will come out to be, the solution y of t will come out to be c1 cos omega t, c1 cos omega t, yes, c2 sin omega t, and plus e will be t, a or b and t plus c3, and z of t will come out to be c2 cos omega t minus c1 sin omega t and plus c4. Now the values of these constants, which are c1, c2, c3, c4, they can be found from the initial position of motion, and in the derivation I have done all the steps, so you need not to worry for that. And finally, the equation, after putting the values of these constants, you will have the equation is equal to y of t is e over omega p and omega t minus sine omega t, while z of t is e or omega b and 1 minus cos omega t. Now I have to go, the equation doesn't look good or being symmetric, but I want to consider some other constant in this one, like E is constant, B is constant, omega is constant, because omega we have already defined is this is equal to QB or N. Now if I do check that what is E over omega B. Now E, I know that this is Newton per Coulomb, while omega is 1/6, while B I have written here that B is Newton per ampere meter. B is Newton per ampere meter. So here I see that Newton is cutting with Newton here, and we have this thing is AM, like ampere meter second ampere meter divided by Coulomb, because here this will go up in Coulomb is in the denominator, so here Now this is second, and this I can write coulomb per second. So F inch, this is coulomb here, and 1 second of this coulomb per second. So coulomb per second work with coulomb second, and we are left with m, and m is the length dimension. So this means if I look at this one, the E would be ratio and then omega. So it is basically the radius of the circle. We define this as r because we have no other length dimension here but r. So I can write that on the radius of the circle is E over omega p, and that our equation will get a decent shape. So I can write that now, not need to write y of t or z of t, I can write y. So y is equal to r and then omega t minus sine omega t, and here the z will come out to be z is equal to r and 1 minus cos omega t. Now if I do multiply this r with this one, so it will come out to be r omega t, and it will be r sine omega t. So in here, if I do multiply this, then it will be r and just really r cos omega t. So if I move this one to this side and similarly this to this side, then I will have the y minus r omega t will be equal to minus r sine omega t. So we have y minus r equal minus r omega t equals to minus r sine omega t, and z minus r equals to minus r L cos omega t. Now if I do square both sides, like taking whole square of this, then whole square of this, and whole square of this and this, and eating the two, then we will have y minus r omega t whole square plus this side z minus r and whole squared. Then on this side it will become r square sine square omega t and r square cos square omega t, and if I take r square common, then sine square omega t plus cos square omega t will give me 1. So this is equal to r squared. And now if I look at this equation, then this equation is somehow similar to the circle equation. Like if I have x minus a whole square plus y minus b whole square, and this is equal to r squared, that it means it is a circle whose center is at AB and whose radius is r. Now here we are not in the xy plane, but we are in the yz plane. So y minus r omega t, so it is a plane, it means it's a circle, and its center is at r omega t in r. So if I want to write in 3 dimensions, that it's a circle whose radius is 0 in x, r omega t, and y and r in z. So it's a circle whose center is Grasma. But it is not a completely a circular motion. It's a sideline motion, or just like a motion when we are having a dot on a moving tire. So that dot basically moves here and here and not completing a circle, but again start from here to here. So it's just like that one semicircle motion, and this we call is the cycloid motion. Now one thing we have to see here, that this motion is really important, and the other thing is we will have to take care of the magnetic force. Now, one thing between E and B here, we say that electric field accelerates a charged particle, means it moves a charged particle, while the magnetic field cannot move a charged particle but can change the direction of motion of the charged particle. So, in other words, we say that electric field can accelerate the charged particle, and magnetic field does not accelerate the charged particle. Then it seems a slight contradiction, because acceleration, and means on the other side we say the magnetic field is changing the direction. So the what is velocity? Velocity is basically the speed and direction. So if direction changes, we say acceleration changes, like velocity changes. And velocity is composed of two things, speed and direction. So why then we say that electric field can accelerate or decelerate a charged particle while magnetic field can't? It only changes the direction of motion. Basically, acceleration, there are two component of this. One you call acceleration, which is the tangential acceleration, and one is the centripetal acceleration. So the axial acceleration, one is the tangential acceleration. Tangential acceleration will call change in speed, while the centripetal acceleration, it will only turn the particle towards the center and it will not change the speed. So that's why we say the magnetic field cannot accelerate or decelerate a charged particle. Its action is only here, while this one is acting on the tangential acceleration. It changes the speed, it changes the acceleration of the particle. So that is one thing you will have to keep in mind. The other thing is that magnetic field does not work. And why is this? Because if I write the equation like why we say, means we have to answer this thing, that why magnetic forces do not work. And if I write the equation of work, means a fraction of work dW is equal to F magnetic dot dl or ds at magnetic dot this, and then F magnetic is huge V cross B, y dl is V E T. Now here is V and here is V. We know that what is the result of this? The result of this V cross B is that we will have a vector which will be perpendicular to V, perpendicular to B, and perpendicular to the plane containing V and B. So it's a perpendicular vector to V. dt is a scalar. So V dot V, two vectors, if they are perpendicular to each other, then their dot product is 0. So the work done by the magnetic force is 0. His magnetic force does not work, and all the magnetic forces do not work. So this is the reason that the force is perpendicular to the direction of motion of the particle. And here further we can say that it's something that seems strange, like for example a fan moving, then we say that current is passing through the coil and it seems like work from the magnetic field. Or if we take the example of a magnetic crane that lifts the car from a place to another place, so we say that magnetic field is at work, but in reality magnetic field do not work, because this is also against the law of conservation of energy. If we take the time derivative of kinetic energy, then it will not change. So this gives a clue that magnetic field, magnetic forces do no work due to their perpendicularity and the force in the direction of motion. So with this, I think this example completes here, and we have the reasons that why it will be a cycloid motion, and um, this motion would be along this one. We have some applications of this thing, like the particle accelerator, the cyclotron or the synchrotron. They are working on this principle. In plasma confinement, we use this geometry, like in tokamaks, in magnetic mirrors, etc. We use these equations. Similarly, in the like in an oscilloscope, in a cathode ray tube, cathode ray oscilloscope, we are having the same application, means dealing with the motion of a charged particle and just generating those shape of the signals. So this is basically due to that one space propulsion is having is this receiving application there. So many practical application connected to the magnetic field, and we do this like even in imaging we are utilizing these equations or such kind of geometry or functions of the electric and magnetic field.